Good morning, I am Seema from BSc Chemistry Honors Final Year. This video is specially for the visually impaired students. Let's start the chapter Metal Ligands Bonding in the Transition Metal Complexes. Transition metals have a very good tendency to form the coordination compounds or complexes, though many attempts were made by the different workers to explain the bonding and the structure of the coordination compounds. The main credit goes to the brilliant work of the Werner. In 1893, the Werner proposed a theory which is commonly known as the Werner's coordinations theory. This was the first successful attempt to explain the bonding in the coordination complexes. In reorganizations of his work in this field, Werner was awarded Nobel Prize in 1913. He explained the bonding in these complexes on the basis of two types of valencies of the metals, which the primary valencies corresponding to the oxidation state and the secondary valency corresponding to the coordination number. The secondary valency or the coordination number determined the stereochemistry of the complexes. However, the Werner's assumptions were not based on the theoretical justification, and the scientists started making attempts to find the basis of the bonding in these complexes. The first attempt in this regard was made by the Sidgwick, who extended the Lewis theory of electron pair bond formation to explain the bonding in the transition metal complexes. He suggested that metal ion atom accepts the electron pairs from the ligands until it achieves the next noble gas configurations and gave a term effective atomic number. En is the total number of the electrons possessed by the central metal ion and the electrons gained by it from the ligands. However, this theory lacked fundamental basis and simply gave emphasis on the stability of inert gas configuration in the coordination compounds. With the evidence advances in these theories of chemical bonding, three modern theories of bonding in transition metal complexes have been developed. These are valence bond theory, crystal field theory, molecular orbital theory. In the present text, we shall discuss many crystal theory of the bonding. The valence bond theory has already been discussed in the previous classes. Valence bond theory. The valence bond theory was developed by Linus Pauling and assumes the bonding between the metal atom or ion and the ligand to be purely covalent. It presents a simple description of the metal ligand bonding using hybrid orbitals of the metal and the electron pairs of the ligands. The basis of valence bond theory is that the appropriate vacant atomic orbitals sp and d of the metal atom hybridize to give a set of hybrid orbitals which are directed towards the ligands according to definite geometry of the complex. The bonding in the metal complexes arise when a metal orbital of the ligand containing a pair of the electrons overlaps with a vacant hybrid orbital on the metal atom or ion, forming a covalent sigma bond called coordinate bond. In addition to a sigma bond, there is also a possibility of pi bond provided suitable orbitals are available on the metal atom and the ligands. The total number of the metal atomic orbitals which undergo the hybridization is equal to the coordination number of the central metal atom or ion. For example, for the coordination number 6 complexes 2d and 1s and 3p orbitals, that is a total of 6 orbitals of the metal atom are involved in the hybridization. The d orbitals involved in the hybridizations may be either inner orbitals or outer orbitals, giving the inner orbitals or outer orbitals complexes. For example, in case of octahedral hybridization, the orbitals may be 1 ns, 3 np and 2 nd, or 1 ns, 3 np and 2, that is the D2sp3 hybridization. Similarly, for coordination number 4 complexes, tetrahedral structure can be considered to rise from bonding with 4 sp3 hybrid orbitals formed by the combination of the 1 ns 3 np atomic orbitals, or square plane structure arising from bonding with 4 dsp2 hybrid orbitals using and 2np atomic orbitals. Some common types of hybridization of atomic orbitals and their geometry. sp hybridization shape is linear, sp2 hybridization trigonal shape, sp3 shape is tetrahedral, dsp2 shape is square planar, dsp3 hybridization trigonal bipyramidal, sp3d square pyramidal, d2sp3 octahedral, Limitations of the valence bond theory. The valence bond theory successfully explained many stereochemical and magnetic properties of the coordination compounds. However, it has many limitations. The main limitations of the VBT are it provides only qualitative explanation for the complexes. It does not explain the color and electronic spectra of the complexes. The theory fails to explain why some metal complex in a particular oxidation state are low spin complex or while some other complexes of the same metal ion in the same oxidation state are high spin. For example, in the complexes cobalt NH36 3 plus and COF6 3 negative. The oxidation state of cobalt is plus 3, but the former is low spin complex and later is high spin complex. It does not predict the relative stability of the different complexes. We know that the certain complexes are level in which the displacement of ligand takes place rapidly, while some are inert in which the ligand displacement by the another ligand is very slow. Valence bond theory does not explain the kinetic inertness of the complex, such as chromium third and low spin cobalt third octahedral complexes. It does not explain the variations of magnetic moment values with the temperature. It does not take into account the splitting of d energy level. It does not predict the relative stability of different structures. The valence bond theory does not predict whether the four coordination complex will be square, planar, or tetrahedral. This can be explained only on the basis of magnetic moment values of the complex. For example, the decision about the geometry of nickel second complexes depend upon the magnetic moment values. For example, nickel second ion has the tonic configuration 3D8. If the complex involves sp3 hybridization, it would have tetrahedral structure. For the formation of tetrahedral structure, the 3D orbitals remain unaffected and the complex is paramagnetic. On the other hand, if the complex involves the dsp hybridization, it would have a planar structure. This is possible if the two unpaired d electrons are paired up there by making the one of the 3D orbital empty. There is thus no unpaired electrons and the complex would be diamagnetic. It also fails to give a satisfactory explanation for the formation of square planar tetraamine copper second ion. The valence bond theory does not tell us why water and halide ions commonly form the high spin complexes while and forms the low spin complexes. To answer some of the above problems, let us discuss other theories. Crystal field theory. The crystal field theory was developed by H. Bette and B. Black. This theory is based on entirely different assumptions than the valence bond theory. As we have already learned, the valence bond theory considered the bonding between the metal ion and the ligand as purely covalent. On the other hand, the crystal field theory considers bond between the metal ion and the ligand as a purely electrostatic. This theory is based on the assumption that the metal ion and the ligand act as a point charges and the interactions between them are purely electrostatic. In the case of negative ligands, the interactions with the metal ions are ion-ion interactions. If the ligand are neutral molecules, the interactions with the metal ion are the ion dipole interactions. For example, in the case of complex ion, the interactions are between cobalt and F negative ions, whereas in cobalt ammonia 6 3 positive, the interactions are between negatively charged and of the ammonia molecules and CO3 positive ions. The central idea of this theory is that the electrons of the metal ion in the environment of other ions or the molecules, as for example within the lattice of a crystal, are affected by the non-spherical electric field stabilized by the surrounding ions or molecules. The electric field was called the crystalline field, but now it is called as crystal field. This is responsible for the name crystal field theory. Basis of the crystal field theory. The basic assumptions of the crystal field theory are: the transition metal ion is surrounded by the ligand with lone pair of the electrons. All type of the ligands are regarded as point charges. The ligands may either ionic or molecules. If the ligand is a neutral molecule, then the negative end of the dipole is oriented towards the metal ion. For example, ammonia is a polar molecule having the charge on the nitrogen and the nilly positive charge is on the hydrogen atom. Similarly, water is also polar with negative charge on the oxygen atom and positive charge on the hydrogen atom. The interactions between the metal ion and the negative ends of the anion is purely electrostatic. The bond between the metal and ligand is considered 100% ionic. The ligand surrounding the metal ion produce the electrical field, and this electrical field influences the energies of the orbitals of the central metal ion, particularly d orbitals. In case of the free metal ion, all the 5d orbitals have the same energy. These orbitals having the same energies are called degenerate orbitals. This means that an electron can occupy any of these 5d orbitals with equal ease. However, on the approach of the ligands, the orbital electrons will be repelled by the lone pair of the ligands. The repulsion will raise the energy of the d orbitals if all the ligands approaching the central metal ion are at equal distance from each of the d orbitals. The energy of each orbitals will increase by the same amount. Therefore, these orbitals will still remain degenerate, but they will have the higher energy than before. But we know that d orbitals have the different orientations, and therefore these orbitals will experience different interactions from the ligands. The orbitals lying in the direction of the ligands will experience greater repulsion, and their energies will be raised to greater extent. On the other hand, the orbitals lying away from the approach of the ligands will have the lesser interactions, and therefore their energy will be raised to lesser extent. Therefore, due to the electrical field of the ligands, the energy of the 5d orbitals will split up. The conversion of the 5 degenerate d orbitals of the metal ion into the different sets of the orbitals having different energies in the presence of the electric field of ligand is called crystal field splitting. This concept forms the basis of the crystal field theory. The number of the ligands and their arrangements around the central metal ion will have the different effects on the relative energies of the 5d orbitals. In other words, the crystal field splitting will be different in different structures with different coordination number. The magnetic properties, spectra, and preference for the particular geometry can be explained in the terms of the splitting of d orbitals in different crystal fields. Thus, to understand the crystal field theory, it is essential to have a clear picture of the disposition of the 5d orbitals in space and geometry arrangements of the ligands around the central metal ion. We may illustrate this concept by considering the complex with the coordination numbers 6 and 4, which are very common shapes of d orbitals. There are 5 d orbitals. These are designated as the dxy, dyz, dzx, dx square minus y square, and dz square. The shapes of these orbitals are described below. The three orbitals dxy, dyz, and dzx are similar, and each consists of the four lobes of higher electron density lying in the x, y, yz, and zx planes respectively. These lobes lies in the between the principal axes. For example, in case of dxy orbitals, the four lobes lie in xy plane in between the x and y. The dx square minus y square orbital has also four lobes of high electron density along the principal axis x and y. It may be noted that this orbital is exactly like dxy orbital, except then it is rotated through the 45-degree around the z-axis. The dz square orbital consists of two lobes along the z-axis with a ring of high electron density in the xy plane. It may noted that although dz square and dx square minus y square orbitals do not look to be similar, yet they are equivalent so far as interactions with the metal ion are concerned. The dz square orbitals can be regarded as a linear combination of two orbitals, dz square minus x square and dz square minus y square, each of which is equivalent to the dx square minus y square orbital. However, it may be noted that these two orbitals dz square and minus x square and dz square minus y square do not have independent existence, but the dz square orbital can be thought of as having the average properties of the two. Since both the orbitals dz square minus s square and dz square minus y square have high electron density along the z-axis, therefore dz square orbitals has a large fraction of the electron density concentrated along the z square. Moreover, one of the component orbitals has lobes along the x-axis, and also the other dz square minus y square has the lobes along along the y-axis. The resultant d orbitals has electron density in xy plane as the Doudna ring or a collar. Crystal field splitting in the octahedral complexes. In octahedral complexes, coordination number 6, the metal ion is at the center of the octahedron and the ligands are at the six corners. The three axes x, y, and z point along the corners of the octahedron and also shown. Let us suppose that the metal ion has a single d electrons, Ti3 positive ions in the free ion. When there are no ligands, the electron can occupy any one of the 5d orbitals because all are of the same energy and are called the degenerate orbitals. However, in the octahedral complexes mx6, all the 5d orbitals will not remain of equal energy. This can be easily understood by the considering the shapes of these orbitals in the octahedral field of the ligands. The comparison of the arrangement of the d orbitals shows that the two lobes of dz square orbitals and four lobes of the dx square minus y square orbital point directly towards the corner of the octahedron, whereas the negative charge of the ligands are concentrated. The remaining three orbitals are orientated in the between the axes. In the case of octahedral complexes, the former two orbitals are designated as easy orbitals while the later three orbitals are designated as the T2G. As the two ligands approach the central ion along the axis, the EG orbitals are repelled more than the T2G orbitals. In the other words, the energy of the dz square and dx square minus y square orbitals increases much more than the energy of the dx square, dyz and dz orbitals. It should be remembered that when a charge is repelled by a similar charge, its potential energy increases. The greater of the repulsion, the greater is the increase in the energy. Thus, in octahedral complexes, the 5d orbital splits into two sets. One set consisting of two orbitals of higher energy Eg orbitals and other set consistent of the three orbitals of the lower energy T2G orbitals. The phenomena of crystal field splitting in an octahedral complex is these two parameters are very commonly used. The magnitude of the delta note varies of the different complexes. The crystal field splitting is also measured in terms of another parameter called dq. The two are related as delta q is equal to 10 dq. It may be noted that the crystal field splitting occurs in such a way that the average energy of the d orbitals does not change. This is known as the barycenter rule, which is similar to the center of gravity type rule. This means that the decrease in the energy of the set of the orbitals that lie at the lower energy level must be balanced by the corresponding increase in the other set. Therefore, in terms of the total energy 10 dq, the energy of each of the two Eg orbitals is raised by 6 dq and the energy of each of the three T2G orbitals is lowered by the 4 dq. In terms of the delta note, the energy of each of the two Eg orbitals is raised by 5 delta naught and the energy of each of the three T2G orbitals is lowered by the 2 by 5 delta naught. The value of 10 dq or delta naught is measured spectroscopically. We observe that initially the energies of all the 5d orbitals are raised equally as shown in state second. This would be observed if the field created by the ligand were spherically symmetrical. However, the energies of the d orbitals splits into two sets because of the different orientations of the orbitals towards the ligands. Crystal field splitization energy. We have learned that in an octahedral field, the energies of 5d orbitals split up. Three orbitals are lowered in energy T2G and two orbitals are raised in energy Eg. We know that the electrons always prefer to occupy an orbital of the lower energy. For example, in the case of neon systems, the d electrons will prefer to occupy at T2G orbitals and is therefore stabilized by an amount equal to the 0.4 delta naught or dq. The amount of stabilizations provided by the splitting of the d orbitals into two levels is called crystal field splitization energy. It is abbreviated as CFSE. Thus, in octahedral field, for each electron entering into the T2G orbitals, the crystal field stabilization is minus 4 q, and for each electron entering into the Eg orbital, the crystal field destabilization energy is plus dc plus 6 decay. Thus, the CFSC is calculated as the algebraic sum of the minus 4 decay per electron in T2G level and plus 6 decay for each electron in the EG orbital. CFSC for various octahedral complexes. For a D1 system, electron will present in any of one of the three T2G orbitals. The electronic configurations may be written as the T2G. The crystal field stabilization energy is minus 4 decay. For a D2 system, the electrons will occupy the T2G orbitals with their spin parallel in accordance with the Hund's rule. The electronic configurations is T2G and crystal field stabilization energy is minus 8 decay. Similarly, for a D3 system, the electronic configurations is T2G3. The crystal field stabilization energy is minus 12 decay. For a D4 systems, there are two possibilities. All the four electrons may occupy the T2G orbitals with one electron gets paired. The electronic configurations may be written as the T2G4. Three electrons occupy T2G orbitals and the fourth electron goes to the one of the EG orbitals. The configurations may be written as T2G3 EG1. The actual configurations may be decided on the basis of delta I naught and pairing energy, that is the energy required to pair the electrons with one another. The configuration is possible if delta I naught is greater than P. These complexes are called strong field complexes because delta I naught is large. In this case, the complex has less number of unpaired electrons and is called low spin complex. The configurations is possible if delta I naught is less than the P. It is called weak field ligand and complexes are called weak field complexes. In that case, the maximum number of electrons remains unpaired and the complex is called high spin complex. As shown above, for a low spin complex having T2G4 configurations, then CFSC is 4 minus 4 decay, that is minus 16 decay. For a system D5, there are two possibilities. All the 5 electrons may occupy the T2G orbitals with 2 orbitals gets paired. The electronic configurations may be written as the T2G5. This is possible if delta I naught is greater than P and the complex will be called the strong field or low spin complex. The 3 electrons occupy the T2G orbitals and 2 electrons occupy the EG orbitals. The electronic configuration may be written as T2G3 EG2. This will be possible if the delta I naught less than the P and the complex is called weak field or high spin complex. The CFSC in these two types of the complex will be strong field, that is delta I naught is greater than P, weak field delta I naught is less than the P. Similarly, D6 and D7 systems have the two possibilities depending upon the relative magnitudes of the crystal field splitting energy and the pairing energy of the electrons. For a D6 systems, that is CO3 positive, cobalt 3 positive ion strong field, that is delta I naught is greater than P, then CFC value will be the minus 24 decay. For a weak field ligand, that is pairing is greater than the delta I naught, then CFSC is value is the minus 4 decay. For a D7 systems, CO2 positive ion strong field ligands delta I naught greater than the P, CFSC value for that minus 18 decay. Weak field for delta I naught is less than the P, for CFSC value is minus 8 decay. D8, D9, D10 systems have only one possible configurations. This is because if we assume the complex to be high spin, the first 5 electrons would go to one each into the 5 d orbitals and the remaining 3, 4 or 5 electrons would fill the TTs and the easy orbitals. But if we assume the complex to be low spin, the first 6 electrons would fill the T2Z orbitals and the remaining 2, 3 or 4 electrons would go into the T2G orbitals. In both cases, the configurations will be the same. Therefore, there is only one possible electronic configurations, D8, D9, D10 systems. The electron configurations for the weak field and strong field of octahedral symmetry are given. The crystal field stabilization energy for a metal ions having the different configurations are assumed. That it is may be noted that for the strong fields, the electrons always pair up in the lower levels first filling it before entering the high energy level for weak filled. Each orbital, whether of high energy, receives the one electron each before any pairing starts. Therefore, weak filled configurations always have same pairing schemes as the free ions as the free ions are available. The next is the crystal field splitting in the tetrahedral complexes. The coordination number for the tetrahedral complexes is 4. The tetrahedral arrangements of the 4 ligands surrounding a metal ion may be visualized by placing the ligands on the 4 of the 8 corners of the cube. The directions x, y, z point to the centers of the faces of the cube. It is clear that the orbitals dx, y, dy, z and dzx point between the x, y, z-axis towards the center of the edges of the cube, whereas the orbitals dx square minus y square and dz square point along the x, y and z-axis, that is to the centers of the faces. It is clear that in tetrahedral field, none of the d orbitals point exactly towards the ligands, and therefore the splitting of the energy will be less than that in the octahedral field. The 3D orbitals dxy, dyz and dzx are pointing close to the direction in which the ligands are approaching, while the two orbitals dx square minus y square dz square are lying in between the ligands. Therefore, the energies of the three orbitals will be raised, while the energies of the two orbitals will be lowered. Thus, in the presence of the tetrahedral field, the degeneracy of the 5d orbitals split up as the two orbitals dx square minus y square and dz square become the stable and their energies are lowered. These are designated as E orbitals. The three orbitals dx, dyz and dzx become unstable and their energies are raised. These are designated as T2 orbitals. It may be noted that for the splitting of the d orbitals in the tetrahedral field, the subscript g is not used. For example, the orbitals dx square minus y square and dz square are designated as the e orbitals, whereas the other three orbitals dx, y, dyz and dzx are designated as T2. This is because a tetrahedral geometry has no center of the symmetry. The symbols G and U have meaning only the for field which is center of the symmetry. The magnitude of crystal field splitting is the difference between the A and T2 orbitals and is designated as delta T, indicating tetrahedral complexes. It is also measured in terms of decay. Delta T is equal to 10 decay. If we compare the magnitude of crystal field splitting in octahedral and tetrahedral complexes having the same metal ion ligands and metal ion ligands distances, it has been observed that the crystal field splitting in tetrahedral complexes is considerably less than in octahedral complexes. It has been found to be delta T is equal to 4.9 delta naught regions for the smaller value of crystal field splitting in tetrahedral than in the octahedral complexes. There are the two main reasons for this. In tetrahedral complexes, there are 4 ligands while there are 6 ligands in octahedral complexes. Therefore, lesser ligands produce less crystal field splitting. The crystal field splitting in tetrahedral field is about two-thirds of the octahedral field. In tetrahedral ligands, in tetrahedral field, none of the orbitals is pointing directly towards the ligands and therefore splitting is less. Since the magnitude of the crystal field splitting in tetrahedral field is quite small and is always less than the pairing energies, therefore the pairing of electron will never be energetically favorable. Thus, all the tetrahedral complexes are high spin complexes. No tetrahedral complex with the low spin has been found to be the exist. It is interesting to note that the splitting pattern is inverted when octahedral is replaced by tetrahedral geometry. CFSC for the tetrahedral complexes. As we know that an electron always prefers to occupy an orbitals of the lower energy since average energies of the d orbitals does not change. Therefore, in terms of the 10 dk, the energy of each of the e orbital is lowered by 6 dk and the energy of the each of the t2 orbital is raised by 4 dk. CFSC is therefore calculated as L algebraic sum of minus 6 dq per electron in the e orbitals and plus 4 dq for each electron in 2d orbitals. In terms of delta T, the energies of each of the e orbitals is lowered by while each of the d2 orbitals is raised by. For example, D1 system, the electronic configuration is even. CFSC value for the D1 is the minus 6 dq. CFSC value for with metal lines having different configurations of the d orbitals in the tetrahedral field. Crystal field splitting in tetragonal and square planar complexes. The splitting of the d orbitals in the tetragonal and square planar complexes can be easily understood from non-splitting of the d orbitals in the octahedral complexes. This is because tetragonal and square planar geometries can be understood by withdrawing two trans ligands from an octahedral complexes. This process is called elongation. Generally, we consider the removal of trans ligands along the z-axis. As the ligands lying on the z-axis are moved away, the ligands in the xy plane tend to approach the central ion more closely. As a result of increase in the metal ligands bonds along z-axis, the repulsion from the ligands to electrons in d square orbitals decrease, and therefore the energy of the dz square orbital is decreased relative to that in octahedral field. At the same time, the metal ligand bond along the x and y are shortened so that the d orbitals in xy plane dx square minus y square experiences greater repulsion from the ligand, and therefore its energy is raised. Similarly, dxy, dxz, dyz orbitals are lowered is raised. The resulting is splitting pattern. This state represents the tetragonally distorted octahedral structures. As the trans ligands lying along z-axis are completely removed, a square planar complex formed. In the square planar complex, there is further rise in the energies of the dx square minus y square and dxy orbitals, and a further fall in the energies of the dz square dxz dyz orbitals. It has been observed that in square planar complex, the energy of the dz square orbitals falls even below the dxy orbitals. The change of an octahedral complex to tetragonally distorted octahedron and finally to square planar arrangements. It may be remembered that the tetragonal distorted structure can also be obtained when the two trans ligands are brought closer to the metal ion. This is called flattening of a octahedron. Shows that elongation of the octahedron. In flattening of octahedron, the two trans metal ligand bonds are shortened, while other four metal ligand bonds becomes larger. The splitting of energies of d orbitals will be reverse of what has been observed in case of the elongations. The next is the crystal field splitting in the trigonal bipyramidal complexes. The coordination number of for the trigonal bipyramidal complex is 5. In trigonal bipyramidal geometry, the three ligands lie along the corners of an equilateral triangle at an angle of 120 degree, each forming the pyramid base in xy plane. The two ligands lie perpendicular to the base triangular along z-axis. It is clear from the that dz square orbitals points exactly towards the ligands, and therefore it will be the most unstable, and hence its energy will raise to the maximum extent. The two d orbitals dx square minus y square and dxy lie in the xy plane. The lobes of these two orbitals do not point exactly towards the ligands but close to the direction in which the ligands are approaching, and hence will be stable in comparison to dz square orbitals, and their energies will be lower. Similarly, the other two orbitals, that is dyz and dzx, lie quite away from the approach of the ligands, and hence will be lowered to greater extent than even dx square minus y square and dxy orbitals. The splitting of the 5d orbitals in trigonal bipyramidal field of the ligands is shown that. Calculate the CFSC value following ions in the octahedral complex is D for strong field octahedral, second D6 weak field, D7 strong field. First is D for strong field, CFSC value will be the D minus 16 dq plus 1 pairing. D6 weak field ligand CFSC value will be the minus 4 dq. Electronic configurations for T2Z Easy one. CFSC value for that minus 18 decaf plus pairing. Calculate the crystal field stabilization energies of the following. D5 strong field octahedral. D5 system strong field octahedral electronic configuration is T2Z5. CFSC value will be the minus 20 decaf plus 2p. D7 weak field electronic configuration is T2Z5 easy 2 and CFSC value for this minus 8 decaf. Factor determining the magnitude of the crystal field splitting. The following factor influences the magnitude of crystal field splitting. First is the nature of the ligand spectrochemical series. The crystal field theory depends upon the nature of the ligands. The greater the ease with which the ligands can approach the metal ion, the greater will be the crystal field splitting goes by it. The ligands which cause only a small degree of crystal field splitting are called weak field ligands, while those which cause a large splitting are called the strong field ligands. Or the spectrochemical series is in an experimental determined series. It is very difficult to explain the order because it incorporates the effects of both sigma and pi bonding. In general, the variations in the splitting is caused by a number of the factors, such as small ligands can cause greater crystal field splitting because they can approach the metal ions closely. For example, F negative ion produces the more delta note value than the large chloride and bromide ion. The ligands containing easily polarizable electron pair will be drawn more easily closely to the metal ion. The ligands which have greater tendency to form the multiple bonds such as cyanide and NO2 negative ions cause the greater crystal field splitting. The very high crystal field splitting produced by cyanide ligands about the double that for a weak field ligands like halide ion. This is attributed to the pi bonding in the metal. The metal donates electrons from a filled T2Z orbitals into the vacant orbitals on the ligand. The following pattern of increasing the sigma donation is observed, that is greater C donors than greater than N, then O, and then the halide donors. The common ligands can be arranged in an increasing order of the crystal field splitting. The regular order is called spectrochemical series. The order remains almost same for different metal ions. The spectrochemical series in the increasing order of the crystal field splitting. In general, the ligand up to the ammonia are called weak field ligands, while those on the right of the ammonia are called strong field ligands. The order of spectrochemical series remains practically same irrespective of the transition metal ions. Oxidation state of the metal ion. The magnitude of the crystal field splitting depends upon the oxidation state of the transition metal ion. The metal ion with the higher oxidation state causes the larger crystal field splitting than in done by the ion with the lower oxidation state. For example, the crystal field splitting energy delta I naught for the COH2 6 complex in which the oxidation state for the cobalt is +3, whereas for the complex in which the oxidation state of the cobalt is +2. Similarly, for the complexes in which iron has oxidation state +3 and +2 respectively, the value of the delta I naught are Gen 13,700 centimeter inverse. This is clear from the following data in which crystal field splitting energies for the hexa-aqua complexes of M2 positive and F3 positive ions of the first transition series. Similarly, for the complex having the other ligands, the delta note value in the lower oxidation states are smaller than the delta note value in higher oxidation states. Type of the d orbitals. The extent of crystal field splitting for the similar complexes of a metal in the same oxidation state increases by about 30 to 50% on going from 3D series to 4D series. The increase in almost of the same amount on going from the 4D series to 5D series. This may be explained on the basis that the 4D orbitals in comparison to 3D orbitals are bigger in size and extend further into the space. As a result, the 4D orbitals can interact more strongly with the ligands and therefore the crystal field splitting is more. Similarly, 5D orbitals are bigger than the 4D orbitals and delta node for the third transition series is more than that of the second transition series. This is evident from the following. Data geometry of the complexes. As mentioned earlier, the crystal field splitting energy of the tetrahedral complex is nearly half the value for the octahedral complexes. In other words, the value of the splitting energy for the tetrahedral complex is generally small as compared to the pairing energy. The tetrahedral complex are therefore mostly high spin complex. For example, show that the d electronic configuration in the following complex CONS6 4 minus 2 FeCN6 4 negative solution in CONS and CS4 2 negative. In this complex ion cobalt is plus 2 oxidation state and D7 system. Its electronic configurations is E40 3 and T2 3 FeCN6 4 negative. In this complex iron is in plus 2 oxidation state and D6 system. Its electronic configurations is T2G6 EZ0. Draw the energy level diagram for PdCN4 2 negative square planar diamagnetic complex showing the d electronic distribution. PdCN4 2 negative is in plus 2 oxidation state. It has d8 electronic configurations. Electronic configuration is dxz square dyz square dz square and dxy square. Thank you.